Okay, Nico, I think we are live.
Okay, so welcome everyone to this Latin American webinars on physics. So we are super happy to have Catarina Cosme today. So she's starting a postdoc in Universidade de Coimbra.
Perfect.
And so we're super happy to have you here, Catarina. So if you want to share your slides.
Yes. Okay, can you see my screen now?
Yes, perfect.
Okay, perfect. Okay. So, thank you so much, Nicolás, for this nice introduction, and I'm really happy to be here to talk to you. And thank you for this to all the organizers. And yeah, today I'm going to tell you about this project, Resonant Stronger Coupling, that was done in collaboration with my colleagues Francesco Costa, who is a PhD student at Göttingen University in Germany, and also Oleg Lebedev, who is a professor at Helsinki University. And this talk is mainly based in these two papers that I have here. So first, I will start by saying a few words about dark matter and dark matter production mechanisms. And then I'll tell you about the features of our model of this resonant stronger coupling. And I would like also to tell you about the phenomenology that we can take from it, in particular direct detection prospects. Then I would like to tell you a little bit about how the temperature evolution of the standard model path can affect our model. And finally, I will conclude. So the first thing that can come to our mind when we think about dark matter is precisely why do we think that dark matter exists, and how do we know that dark matter exists? And in fact, there are several phenomena that point towards the existence of dark matter. For instance, we have the case of the galaxy rotation curves that are just a plot of the orbital velocity of a gas or a star within a galaxy as a function of its radial distance from the galactic center. And from what we observed from the luminous matter, we would expect that these galaxy rotation curves will go down as we go far away from the galactic center. And actually, this is very intuitive. And just by Newtonian mechanics, for instance, we can compute the orbital velocity, and we can see that it goes with the square root of the inverse of the radial distance from the galactic center. However, what we really observe in the universe is that these galaxy rotation curves are not going down as we go far away from the galactic center, and instead of that, they become almost flat. So this means that there must be something else, some kind of non-luminous matter that is accounting for this effect. And since we cannot see it, we call it dark matter. Also, there is information that comes from the baryon acoustic oscillations of the cosmic microwave background, so the CMB. And these baryon acoustic oscillations are just small ripples in the CMB due to temperature fluctuations whose peak structure can only be explained if we add dark matter to the model. And then we have probably one of the best evidence for the existence of dark matter, that is the bullet cluster, that is depicted here in this picture. So the bullet cluster is a huge system of galaxies that was formed when two big clusters of galaxies collided. And in these two pink clumps here, we can see where the baryonic mass of the system is localized. So the hot gas of the bullet cluster is mainly localized here. And it was found using, for instance, the Chandra telescope in the X-rays. And then the idea was to find where the major part of the mass of the system was localized. And therefore, to do that, they used other techniques, other telescopes that would see in another ranges of the electromagnetic spectrum. And they used, for instance, the so-called gravitational lensing, that is when we have light that is traveling in the universe and it is bended due to the intervening matter. And so they could find that the major part of the mass of the system was localized in these two blue regions here. So we can see that the pink and the blue regions, they do not overlap, which means that the major part of the mass of the system is not baryonic mass. It must be something else that we call dark matter. Also, from the observations of the CMB and large-scale structure, we know that dark matter makes up about 27% of the mass energy content of the universe, while baryonic matter is just about 5%. And then we have a huge slice of this mass energy budget of the universe that is dark energy. And this dark energy is responsible, for instance, for the recent accelerated expansion of the universe. And also, we know that a dark matter candidate should fulfill some requirements. For instance, we know that it has to be stable, or at least very long-lived, otherwise we wouldn't have dark matter by now. This dark matter candidate has to be cold, non-relativistic, in order not to spoil the structure formation. For instance, how galaxies are formed. Also, it has to have very small interaction with the electromagnetic field, or no interaction at all. It's dark. And of course, this dark matter candidate, its abundance has to match the abundance of dark matter that we observe today. And so from this list, we know that nothing in the standard model fits the description, so dark matter should consist of a new particle or a new set of particles. And okay, so actually we already know few things about dark matter. So we know that there is evidence for the existence of dark matter. We know the amount of dark matter that is out there, and we know more or less how a dark matter candidate should look like. However, there is a fundamental question that still remains, that is, what is dark matter made of? What is its nature? And the honest answer is that we still don't know, despite the large number of dark matter candidates that we can find in the literature. And so this talk will be about one of these dark matter candidates, a specific one. But before going to the main topic of my talk, I would like to tell you a little bit more about one of the most popular dark matter production mechanisms, where dark matter is produced thermally, so that we can see the shortcomings of this dark matter production mechanism, of these dark matter candidates, and see why we need to look for an alternative to it, and how our model can be a good alternative to this more popular dark matter production mechanism. And so let's start. So one of the most well-known and well-studied dark matter production mechanisms is the so-called freeze-out mechanism. So the freeze-out mechanism assumes that dark matter, which I represent here by this X, was in thermal equilibrium with the standard model particles in the early universe. So this means that standard model particles were producing dark matter, and dark matter was producing standard model particles. So there was this thermal equilibrium between these two sectors. And I guess that the best way to explain to you this freeze-out mechanism is to give you a plot. And so in this plot, we have the yield of dark matter, that is just a ratio between the number abundance of dark matter over the entropy density of the universe, this little s, as a function of this x parameter, that is just the mass of dark matter over the temperature. So this dashed line corresponds to the equilibrium yield of dark matter. So this means that if dark matter is in thermal equilibrium, its yield should follow this dashed line. And then we have here different colors corresponding to different final yields of dark matter, depending on the dark matter coupling lambda to the standard model. And basically, if we want to build a plot like this, we have to solve the Boltzmann equation that is stated here. And so in this left-hand side of the Boltzmann equation, we have basically how the number abundance of dark matter will evolve in the universe. So this h is the Hubble parameter. And then we have the right-hand side that is the so-called collision term. And the collision term tells us about the production and destruction of dark matter in the universe. So here I'm assuming the simplest case of freeze-out mechanism that we can have, that is just considering annihilations and inverse annihilations of dark matter. So this sigma b is the thermally average cross-section. EQ stands for equilibrium. And according to this freeze-out mechanism, the initial abundance of dark matter, initially the dark matter is in thermal equilibrium with the standard model particles. So we can see that its yield follows the dashed line. And just when the interaction rate between the dark and the visible sectors, this capital gamma x, becomes smaller than the Hubble parameter, which means that virtually no particles are being created or destroyed within a Hubble time, the dark matter will decouple from the thermal path and its abundance becomes constant. So we say that at this point, dark matter has frozen out. So since the typical cross-section that provides the observed dark matter abundance in this case is of the order of the weak scale, we call this dark matter candidate WIMPs, weakly interacting massive particles, and we can show that, for instance, the present dark matter abundance, this omega x naught, is proportional to the inverse of the dark matter coupling lambda. So this means that smaller couplings will provide larger abundances of dark matter, or accordingly larger yields of dark matter, because the yield and the abundance, they are directly proportional. And that's something that we can see here in this plot. So for instance, let's focus on this blue line. This coupling is the smallest one of these three, and it's the one that is providing the largest yield of dark matter. Of course, that these couplings are really large, but this is just for illustrative purposes. And okay, so WIMPs are very popular, and in fact, almost all dark matter detection experiments were designed to catch them, but there is a huge problem. And the problem is that these WIMPs have not been detected so far. And now the parameter space of these WIMPs models is very constrained by experiments. And just to make my point, I decided to put here 3 different WIMP dark matter scenarios. So these plots come from this recent review paper from yesterday. Actually, it's funny because yesterday I had the slide with the plots from the previous paper of these same authors, but then I saw the paper and I decided to update also these plots. And so here in the left-hand side plot, I have the WIMP scalar dark matter through the Higgs portal. In the middle, WIMP fermionic dark matter through the Higgs portal. And on the right-hand side, I have WIMP scalar dark matter through Z prime portal. And in the y-axis, in these two, we have the dark matter coupling to the portal or to the standard model particles, because here the Higgs is the particle making the connection as a function of the dark matter mass. And here we have the dark matter mass as a function of the Z prime mass, but it's just a way of representing the results. And so in all of them, this red curve, this red line corresponds to the parameter space of the model that can provide the observed dark matter abundance. And then we have these colored regions that correspond to exclusion regions. For instance, in this case, the blue one, the parameter space of the model is excluded by direct detection experiments. And so we can see that in these 3 models of WIMP dark matter, these models are completely ruled out. So maybe in this WIMP scalar dark matter through the Higgs portal, in the region of the resonance, we still have some hope of finding dark matter or finding WIMPs, but still the parameter space is very constrained. And although these are amongst the simplest models of WIMPs that we can have, the thing is that this happens for other WIMPs models. And so maybe this means that the WIMP is waning, and maybe this means that we need to look for an alternative to this freeze-out mechanism. And an alternative to this freeze-out mechanism can be done by just relaxing this initial assumption of thermal equilibrium. And if we do so, we can talk about the freezing mechanism. So the freezing mechanism assumes that dark matter was never in thermal equilibrium with the standard model particles, which means that in the early universe, standard model particles were producing dark matter, but there is almost no back reaction from the dark sector. So the production of particles occurs mainly in this way. And again, the best way to explain to you the freezing mechanism is with a plot. And we have the yield of dark matter again as a function of this X parameter. The dashed line corresponds to the equilibrium yield. And then we have different colors corresponding to different final yields of dark matter, depending on the dark matter coupling lambda. And again, if we want to track the evolution of the dark matter number density or the yield in the universe, we have to solve the Boltzmann equation. And we can see that the left-hand side is exactly the same as the left-hand side of the freeze-out case, but the collision term is different. And it is different because the initial conditions for the freezing mechanism are totally different from the initial conditions of freeze-out. And here I'm also assuming the simplest case that we can have for freezing, that is considering that there is a generic sigma particle, that is a standard model particle, that is decaying into dark matter. And so this m sigma is the mass of this particle. K1 and K2 are modified Bessel functions. And according to the freezing mechanism, initially the abundance of dark matter is very small, or it is 0, and then it is increasing due to the decays of this sigma particle into dark matter. And just when there is no more energy of these sigma particles to produce dark matter, or the number abundance of these sigma particles is very small, at that point the production stops and the yield of dark matter becomes constant. So we say that at this point dark matter has frozen in. So since in this case, the typical couplings that provide the observed dark matter abundance are very small, very feeble, we call these dark matter candidates FIMPs, feeble interacting massive particles. And in this case, in the case of freezing, usually all the processes that can contribute for the dark matter production, the interaction rates will always be smaller than the Hubble parameter. In this case, the abundance of dark matter is proportional to the dark matter coupling lambda, which means that larger couplings will also provide larger yields of dark matter. And that's something that we can also see here in the plot. So for instance, in this case, the blue one is the one with the largest coupling, and it's also the one that will provide the largest yield of dark matter. So this is basically freezing in a nutshell. And just to wrap up this part, I prepared this slide with the main differences between the freeze out and the freezing mechanism. So freeze out, dark matter initially in thermal equilibrium with the standard model of particles, and just when the interaction rate becomes smaller than the Hubble parameter, it decouples from the thermal bath and its abundance becomes constant. In this case, the abundance of dark matter is proportional to the inverse of the dark matter coupling lambda, but the big problem is that WIMPs have not been detected so far, and now the parameter space of this model is very constrained by experiments. In the case of freezing, dark matter was never in thermal equilibrium with the standard model of particles. In this case, the abundance of dark matter is proportional to the dark matter coupling lambda, which means that from here we can see that we will need smaller couplings when compared to the freeze-out case in order to attain the observed dark matter abundance. And on the one hand, if we need smaller couplings, this can be very good because this means that WIMPs can evade the stringent observational constraints that WIMPs cannot do anymore. But on the other hand, this can also be very bad because with such small couplings, this means that WIMPs are really hard to probe in detection experiments. But in any case, in our model, we decided to go within this freezing framework. And okay, so it seems that WIMPs or the freezing mechanism is a very good alternative to the freeze-out mechanism. At least it's not that constrained, but actually it faces two main challenges. And one of them is that, as I told you before, usually it has very small couplings, which makes detection of usual models of WIMPs really hard. It's hell. And then it has an initial assumption. So it assumes that initially the abundance of dark matter in the early universe is zero or negligible, which may not be completely true, as we will see in the next slides. But okay, the big question now is how can we probe WIMPs? Is there a way of probing or detecting such elusive dark matter particles? But before trying to answer to this question with our model, let me just take one step back and tell you a little bit more about this second bullet that we have here. Because in fact, assuming that dark matter, the abundance of dark matter in the early universe is zero or negligible, it is a quite strong assumption in a world with gravity, because we know that there are some processes that can produce lots of particles, and in particular stable scalars, that can be viable dark matter candidates in the early universe, and just through gravitational interactions. And so just to exemplify, I have here 4 models. So for instance, during inflation, we can have scalar fluctuations that can produce stable scalars and dark relics. Right after inflation, we will have a period that is called reheating. And so during this reheating phase, basically what happens is that the inflaton will transfer its energy to the standard model of particles, and there is a phase where it will start to oscillate, and during these oscillations it can produce lots of particles, can produce standard model particles and other particles like dark matter. Also, we have the case of the inflaton decay and the freezing itself. And the thing is that during this production, this gravitational production, usually the particles have very small couplings, very feeble couplings, so they will never achieve thermal equilibrium, and therefore we can end up with an important background of dark relics that will be important for the non-thermal dark matter studies. And the thing is that we have to take into account all the dark matter production from these processes that are non-thermal, and we'll have to add up, so we can have even an overabundance of dark matter. And the thing is that even if there are no direct coupling between these dark scalars or these stable scalars and the inflaton or the standard model particles, we can still have them being produced by gravity, because we cannot turn off gravity, and therefore this will be present in the early universe. And just to make my point, I decided to talk very briefly about 2 of these production mechanisms. So here I just have the timeline of the events. We have inflation, and that will stop or will end at this Tn temperature. And the thing is that although the inflaton has to be the field with the dominant energy density, because it's the one that will drive inflation, there is also possibility of having other scalars during inflation. So the only thing is that its energy have to be subdominant, but it is possible, and there are several beyond standard model theories that predict the existence of scalars during inflation. And so let's focus on one of these scalars that I will call S. So this is the potential for this particle. We have the self-interaction coupling, lambda S, that usually is very small. We have the mass term. Usually it will never achieve thermal equilibrium. But the thing is that any scalar field during inflation will exhibit quantum fluctuations, and these quantum fluctuations will get stretched and amplified just by expansion. And therefore, these quantum fluctuations will provide an initial amplitude for the field at the end of inflation. So what happens is that usually the field remains frozen with this initial amplitude that is provided by the quantum fluctuations, and the field will start to oscillate when its mass is of the order of the Hubble parameter. And in particular, if the potential is a quadratic one, we can show that it will behave like matter. So we have a non-relativistic component, and if it has the observed dark matter abundance, it is a viable dark matter candidate. And therefore, we are left with a long-lived oscillating scalar condensate that can survive until today. And here, we don't even need a direct coupling between the inflaton and dark matter. We just need gravity. And actually, during my PhD, I studied these dark matter candidates, these oscillating scalar fields as dark matter candidates, whose initial conditions were set by the inflationary dynamics. So I studied with my PhD supervisors and also people from Helsinki. But also, even after inflation, when we have the period that is called reheating, what happens is that during this reheating, as I told you, the inflaton will transfer its energy to the standard model of particles, and there is a first phase of the reheating that is called the preheating. And this preheating physics is quite involved, but basically what happens is that so the inflaton will roll to the minimum of its potential, and it will start to oscillate. And imagine if there are couplings to other scalar particles, these oscillations of the inflaton, they will produce a resonant amplification of the amplitude of these scalars that are present also in the system. And therefore, there will be a huge production of particles. And so we can have also lots of dark relics or stable scalars that are produced via these inflaton oscillations. But again, even if there is no direct coupling between the inflaton and this kind of scalars, since the inflaton is oscillating, the scale factor will also oscillate, and consequently the Hubble parameter as well. And this can induce some terms in the Lagrangian of this form. And this can be seen as the annihilation of the inflaton oscillations into these S particles. And again, there is no need to have direct coupling between the inflaton and these S particles. And for instance, this phenomena was studied by this Japanese group and also by BioLab. And so, okay, so these are just two examples. And the thing is that we can end up with a huge amount of dark relics. And now the question is, how can we avoid the overproduction of dark matter? Or in other words, how can we get rid of the excess of these dark relics? And in fact, one interesting answer relies precisely in this feature of the inflaton, because we know that the inflaton will start to oscillate around the minimum of its potential. And basically, if it is oscillating around the minimum of a quadratic potential, it will behave like matter. And since the inflaton is still the one that is dominating the energy density during reheating, we can have an early matter era here. And having early matter eras before the usual radiation era, it's interesting because in this part, the Hubble parameter will scale with a scale factor with a different power, different from when we have just pure radiation. There is also, of course, entropy injection in our universe. And therefore, what happens is that the dark relics that were formed in the early universe can be diluted. And in particular, we can compute the dilution factor that will depend on the square root of the Hubble parameter computed at the end of inflation and the Hubble parameter computed at this reheating temperature. So the reheating temperature is defined when all the energy density of the inflaton went to the energy density of radiation. So that would be the reheating temperature. Or also we can define this is equal to say that the dilution factor is just the ratio between this Tn and this Tr. And the thing is that the larger the dilution factor, the longer the early matter domination that we can have. And also, since we have this longer early matter domination era, we can have lower reheating temperatures for our universe. So having this early matter era is useful because one, then the assumption of nearly zero dark matter abundance in the early universe for the freezing case is satisfied, and it also can provide lower reheating temperatures. And this can be very useful for our purposes, because in our model, we decided to study the case of freezing dark matter production, but just in the range where the dark matter mass is larger than the reheating temperature. And therefore, we have a justification for having low reheating temperatures in our universe. The only thing is that this DR is, as always, to be larger than 4 MeV, because we don't want to spoil the BPN predictions. But okay, so why is it interesting to study this parameter space? So dark matter mass is larger than the reheating temperature. And it is interesting because in this case, the only particles of the standard model that will have energy enough to produce dark matter are the ones that are at the tail of the Boltzmann distribution. And therefore, this means that the production of dark matter will be Boltzmann suppressed. Therefore, if the production of dark matter is Boltzmann suppressed, this means that we will need larger couplings in order to compensate for this Boltzmann suppression and to achieve the observed dark matter abundance. And so, if in the case of freezing we can have larger couplings, maybe these models can become testable in detection experiments. And that's what I want to show you. And so for this model, for this work, we decided to pick one of the simplest dark matter models that we can have, that is the scalar dark matter through the Higgs portal. So here I just have the mass term, and the lambda HS is the coupling between dark matter and the Higgs, and consequently between dark matter and the standard model. We are assuming the case, again, where the dark matter mass is always larger or much larger than the reheating temperature. And then if we want to know the abundance of dark matter that our model is able to provide, we have to solve the Boltzmann equation. So here, the only processes that will contribute for the dark matter production will be the Higgs annihilating into dark matter. So the Higgs annihilating into this S particle. And then we can also have the inverse process. So dark matter annihilating into Higgs. And so these capital sigmas are just reaction rates and are defined in this way. So cross section times the number density squared. And in our computations, we solved always the full Boltzmann equation. But of course, we can think about some limits. And actually, there is a parameter space of our model where, for instance, the annihilation dark matter term is very inefficient. And therefore, we are just left with Higgs annihilating into dark matter and then almost no back reaction from the dark sector. And therefore, we are in the freezing regime. And then we just need to solve the Boltzmann equation. The integration parameter will be the temperature. So we will integrate from the reheating temperature until now, assuming that at reheating, the initial abundance of dark matter is 0. Then we can get an expression for the yield of dark matter. And notice that here we have this exponential, that is precisely the Boltzmann suppression of our model. So the abundance of dark matter is being Boltzmann suppressed. But then if we assume that this S can make all dark matter in the universe, what we have to do is to equate the yield that our model can provide with the observed yield of dark matter. And if we do so, we can get an expression for the dark matter coupling, lambda H, that depends on the dark matter mass and also on the reheating temperature. So actually, we can see that here we have a very small prefactor. However, since we are always working in the parameter space where the dark matter mass is much larger than the reheating temperature, the smallness of this prefactor can be easily compensated by this exponential factor. And in this case, we can have couplings of almost order 1 or order 0.1, which is really nice for these freezing models, and in particular for this Higgs portal. But okay, as I told you, we always solved the full equation. And of course, there is also a possibility for our model to have thermalized dark matter, to have WIMPs. But for that to happen, these two interaction rates, so the production and the annihilation reaction rates, have to be equal, and they have to be active at the same time for a long period of time. And if that happens, the system can thermalize and we can have the freeze-out case. And just to show you the different regimes that we can have in our model, let me just show you a few plots. So in this plot on the left-hand side panel, we have the reaction rate as a function of the temperature. In green, the reaction rate of the Higgs annihilating into scalars. In yellow, the dark matter annihilating into Higgs. And then we have in blue the Hubble parameter term, just because we always want to compare these rates with the expansion rate of the universe to see efficiency. And in the right-hand side, I have the yield of dark matter as a function of the temperature, and this dashed line is the equilibrium yield. And for instance, for this parameter space, for this reheating temperature, mass of dark matter, and couplings, we can see that the annihilation rate was always below the Hubble parameter term, and therefore, and also it was not equal for a long period to this production rate. So in this case, the system will never thermalize, and we have the freezing regime. And we can see, for instance, that this plot is very similar to the plot of the freezing that I showed you in the beginning. For instance, for this parameter space here, we can see that the annihilation rate was a little bit above the Hubble parameter term, but still it was not equal at the same time to the production rate, and therefore here we still have the freezing, but it will be very close to the freeze out case for this parameter space. And finally, we have this situation where we can see that the annihilation and the production rates, they are equal and they are active at the same time for an extended period. And in this case, the system can thermalize and we can have the freeze out in our model. So notice, for instance, that here we have the yield of dark matter following the dashed line, the equilibrium yield, and then it decouples and the yield becomes constant. So the usual freeze out regime. So this was just to show you the different regimes that we can have in our model. And now let me tell you about the detection prospects, and in particular, the direct detection prospects. And so in this model, I represent the dark matter coupling as a function of the dark matter mass. These colored lines correspond to the parameter space of our model that can provide observed dark matter abundance. And then in these almost vertical lines, we have the case of freezing, while in this purple one, we have the case of freeze out. So in the case of freezing, we have different reheating temperatures here. And this dashed line corresponds to the limit of the neutrino fog or the neutrino floor. And so these almost vertical lines, we can show that they follow exactly that expression for the dark matter coupling that I showed you before for the case of freezing, while in the case of freeze out, the dark matter coupling will not depend on the reheating temperature, on the temperature basically. So it will be proportional to the dark matter mass. And this shaded region corresponds to the region that can be already proved with data that comes from LZ 2022. And so the main message from this plot that we can take is that our freezing model can already be proved by direct detection experiments, as we can see here. And actually, we can see that in this case of freezing, we have couplings of almost order 0.1 here, and almost order 1, but it's not possible yet to reach here. So we could get very large couplings actually, and this is just because the Boltzmann suppression. But notice that if we were thinking about conventional freezing, so with usual reheating temperature much larger than the dark matter mass, we would get couplings for the Higgs portal of the order of 10 to the minus 11, which would be really low here. So it would be almost impossible to detect them. But we've seen that in this model, it can already be proved with the direct detection experiments. And okay, so now I could stop here my talk, but I would like to tell you about one more detail, that is the following. So far I was considering that dark matter, or we were considering that dark matter was produced almost around the reheating temperature, but basically we were considering the dark matter abundance that was produced in this branch for the temperature evolution of our universe. However, we know that there is more story behind this reheating temperature. And actually, there are some models of the inflaton transferring its energy to the standard model, where we can have a maximal temperature for the universe that can be really large or larger than this reheating temperature. And so in this first paper that we did, we assumed that all dark matter that was produced in this branch would be completely negligible. However, in some talks that my collaborators and we gave, and also at least one referee, they were asking if this was a good assumption. And in fact, so we decided to be a little bit more complete. And therefore, for this second paper, we decided to do a more careful study of the standard model evolution, standard model temperature evolution, and see if it would be significant to take into account the dark matter that was produced in this branch, especially for the plot of the detection prospects. And so actually in the early universe, there are many things that we really don't know, but we tend to think that in the early universe, the energy density of the inflaton is transferred directly to the energy density of the standard model particles. And that's what we have here. So here I have the energy density of the inflaton as a function of the scale vector, the inflaton in blue, and the energy density of the standard model in yellow. And so in the early universe, the energy density of the standard model is 0, negligible, and then it's increasing until it reaches a maximum. And then the energy density of the inflaton is decaying, and also the energy density of the standard model is decaying. At this temperature here, at this point, the inflaton is completely decayed, let's say decayed completely. And then also the energy density of the standard model continues to decay with a different slope, basically because here we have injection of entropy and here entropy is constant. But since we have the standard model will be mainly radiation, what happens is that the maximum of this energy density of the standard model will also correspond to a maximal temperature for our universe. And this maximal temperature could be much larger than the reheating temperature, and they can be actually very different. And this will not be the good framework for our scenario because we will need larger reheating temperatures, for instance, or lower reheating temperatures and also lower maximal temperatures. But we can think about our other framework, and another framework would be thinking that the transfer of the energy of the inflaton to the standard model is not direct, but it happens in 2 steps. So first we have the energy density of the inflaton, or the energy of the inflaton transferring to these particles, and then the energy of these particles is going to be transferred to the standard model particles. And one good intermediate particle could be the right-handed neutrinos. And here I have the energy density of the right-handed neutrinos. And what happens in this case is that the energy of the inflaton is being transferred to the right-handed neutrinos, but not directly here to the standard model. And then the energy of these right-handed neutrinos is transferred to the standard model. And in this case, what happens is that we can have the standard model energy density will reach a maximum, and it will reach a plateau, and it will be constant or always constant until the point where, for instance, in this case, the inflaton has transferred all its energy, and then to the point where also the right-handed neutrinos have transferred all their energy. And therefore we can have maximal temperatures that are really close to the reheating temperature. And in particular, we can also have a model for having lowered these T-maximal temperatures of the universe. And that's precisely what we needed. And in particular, if the decay width of the inflaton is very close to the decay width of the right-handed neutrinos, or if it is similar, what happens is that the T-maximal will precisely coincide with the reheating temperature, because these 2 particles will decay at the same time. And that's what we were thinking for our model. So here I just have a plot for the temperature, the evolution of the temperature. So again, since the standard model is pure radiation, and if its energy density is constant, this means that the temperature will also be constant. And then at some point it starts to decay. And so in our first paper, what we did was to compute the abundance of dark matter in this branch. And now we want to add the other contribution, that is the all dark matter that can be produced in this branch. And that's basically what I have here to compute the total dark matter particle number. So here we add the 2 contributions. And again, it's just following the same recipe. We have to solve the Boltzmann equation, and then we can get the yield of dark matter. that the yield for this new paper will be basically the yield, the result for the yield of the previous paper with the relabeling of TR to Tmax, but in any case, these two temperatures are the same. And then times this factor here. And then let me just show you our updated plot for the direct detection prospects. So here again, we have the dark matter coupling as a function of the dark matter mass. In the case of freeze out, there is no difference because it will never depend on the reheating temperature or on this maximal temperature. But we can see that there is a small shift, a modest shift between our previous results and this now more complete paper. And so this thin line corresponds to the case to our previous paper. So the result for the dark matter coupling as a function of the dark matter mass and the reheating temperature for the first paper, and the thick line corresponds to our new paper. And therefore, we can see that there is just a modest shift. And actually, if we fix the reheating temperature, we will just need an increase in the dark matter mass when compared to the previous paper of about 5% in order to get the observed dark matter dependence. And okay, so but we can see that the final results will not be changed, and our conclusions were already fine in the first paper. So there is no much change, but we can see that. So okay, the second paper is more careful, and we have a more dedicated study. And then this brings me to my conclusion. So I told you that okay, there are processes in the early universe that can produce dark relics gravitationally. They can be produced a lot. But if we have an early matter era, we can like wash out these dark relics, and therefore the assumption of initial zero abundance for dark matter for the freezing will be satisfied. And also when we have this early matter era, we can have lower reheating temperatures for our universe. In this case, we studied the Higgs portal dark matter, where dark matter is produced via freezing. But we were interested in the case where the dark matter mass is always larger than the reheating temperature, because in this case, we could see that dark matter production will be Boltzmann-suppressed, so we will need larger couplings. And if we need larger couplings, we could see, for the case of freezing, we could see that this model could be already tested by direct detection experiments like LZ. And there are forthcoming data from other experiments or next generation experiments of dark matter, like Zenon and Ton and Darwin, that will be able to prove even lower couplings of dark matter. And that's it. So thank you a lot for your attention.
Excellent. Thank you very much, Catarina. Super nice talk. Are there questions or comments? I think Javier has a question. I have one. I think Javier just shy. So if you go back a couple of slides when you show previous one, I think.
This one.
Yes. No, the one where you have the constant temperature. So I have if I understood correctly, so here you don't care about the duration of this of this plateau, right? For the temperature, you just want the Tmax to be T reheat, right?
Yes,
but why is independent of the duration? Do you have an intuition?
I think it will depend, of course, always on this decay width that you have here. So probably for other values here, you will have a different duration. But our idea, for instance, in this case, for this particular plot was to get a reheating temperature that will be around 100 GeVs. And we found that those were the values that would match. And therefore, we will have this duration for the plateau. But of course, it will depend on the reheating temperature that you want and also on these two decay widths, I would say.
But okay, but I think you can tune these parameters to have like a longer or smaller plateau, right?
Plateau duration. Yeah, probably you can do it. But now I'm not.
But do you think
I cannot tell you immediately how to do it. I think.
But no, but I don't care about the numbers of the width. But just would like to understand if you have an intuition of what will happen in that case, because I mean I don't know if you expect a a dependence on the duration of the plateau or not?
No,
I
we don't expect really, I think, duration of the plateau. We just needed a smaller, for instance, reheating temperature, and that the maximal temperature would be closer to the reheating temperature. But I think we are not really interested on that because, as we've seen, so even when we compute the dark matter abundance that was produced here, it was not that significant. So having this larger or a bit smaller will not change that much the results, I think.
Okay, I see. Thanks.
No.
Are there further questions? Okay, I have another one. Good.
Oh,
No,
okay, go ahead,
go ahead,
Nicolás.
please,
Go
please.
ahead. Okay, so your results are for scalar dark matter. So if you change the nature of dark matter, how would you think your results would be modified?
We just studied the simplest case, but I think if it is like fermionic dark matter, probably it will not change a lot. Although I will need to study it very well because basically this model is very dependent on this Boltzmann suppression that we can have. And so I think it will not change that much if it is another kind of dark matter.
Okay, thank you.
And if instead of a plateau you get a rising temperature during reheating, nothing will have changed, or do you expect something?
Like in this case, for instance.
No, here in these two, yes, there is decreasing, right? The temperature.
Yes.
You can imagine a scenario where it increases.
But doing something like this and go down, you're saying?
Well, here is like plateau, I mean, constant, and then goes down.
Yes.
You can imagine that instead of being constant, it goes up.
Probably, I don't know, probably it will change a little bit, but I think the main plot will not change that much because actually we can also have the scenario where, well, it will not correspond completely to an increase, but we can have, even in the plateau, we can have T maximal, and then we have T reheating that are a bit different. But even in that case, we checked that it will not change that much, the results.
Okay, thanks. Any further questions or comments to Catarina? So I have one more, if I may. Yes, you can. Thanks. So in the so you focus on direct detection, but I think indirect detection as well could be there, no?
Actually, we were discussing this with Oleg, and the thing is that in this Higgs portal case, the direct detection has better, we can probe better the couplings than indirect detection. So we decided to show just the direct detection.
Okay.
In the Higgs portal, at least.
Sorry, so the next question is the next question would be, what is the interplay with colliders? No, because for these large couplings, maybe you could have bounds from, I don't know, monojet searches or things like this. I don't know which region of the parameter space the searches are sensitive to.
Yeah, for colliders, I have no clue, to be honest. But yeah, probably it would also be possible to probe this dark matter candidate with colliders. Yes, that's something that we can see. Thank you.
I think in this model the only probe will be the invisible decay of the Higgs, but the smaller masses.
For the smaller masses, but probably it will not be competitive, like comparing with the direct detection in this case, or do you think it will be still?
Yeah, maybe not.
Here, because I don't know. I will have to check, but probably it's not that competitive with at least this part of direct detection.
No, you have to go to
for Higgs invisible grid, for light enough masses, they always win, no? Because then the direct detection will go up, no?
Okay.
But I was wondering about the other ones, like monojet.
Monojets, yeah, that I don't know.
No idea.
Yeah, but that's something that I can look it up. Thank you.
And here you avoid the Higgs resonance and light dark matter masses because the cross section becomes a mess. Or
Yeah.
is there another particular reason?
In this case, like basically the question is why we are just considering these large masses for dark matter, not light.
Yeah, right.
So basically it was, I think, just to have masses much larger than the reheating temperature, because the minimum temperature that you can have for reheating is 4 MeV. So we were thinking about larger masses in order to see this suppression, I would say.
Yeah, but 1 GeV is higher than 4
Yes, it's
GeVs.
our, but well, we decided to choose this parameter space.
Yeah.
I don't think there was a more deep reason to do that. I don't think so. I think we just decided to stick with this. Yes.
And maybe last question.
No
For
worries.
instance, the figure, the line of a 10 GeV, still heat equal to 10 GeV, the one on the very left.
Yes.
So that corresponds to a dark matter mass of like 200 GeVs.
Yes.
So if you think in a term of WIM and the X freeze out order 20 as usual, something like this. So that corresponds to a freeze out of around 10 GeVs as well. So
Yes.
you're not kind of in I mean, are you sure that you're always having freeze out in radiation? Or you could have a freeze out in
matter era.
during the reheating. Yeah.
The reheating.
Because it's kind of borderline, right?
Yes, it's very borderline. But I think this still this already corresponds to radiation era, but I can check it as well. But I think it still it is in radiation, I think.
Okay. Excellent. So I don't see
Yeah, I have a question.
other question.
Yes.
Please, Robert.
I was waiting for the for the window for asking. Yeah, I was wondering because very interesting the webinar and the mechanism. But I was wondering in the case in which your dark sector may be more complex that only one scalar as dark matter. I mean, in the sense that you have other particles in the dark sector. I was wondering what would be the role of, for instance, coannihilation or something like that, because in the case of freeze out, coannihilation also can affect the relic abundance because of the close, the two dark particles that are close in mass. In this scenario, also maybe modify the final output in the case that you have a degenerate dark sector or something like that, because of the
Yeah, probably if we have other particles in dark sectors, yes, I think the results will change a little bit, I would say. But yeah, it's a different process that I have to think more about that to give you a concrete answer to that. But yeah, I think probably the results will change. Yeah, because we could have co-annihilations and everything. Yeah, but it's also interesting to think about it. Thank you.
Yeah, because I don't remember well. In the case of coannihilation, you need to have a lower coupling constant or higher coupling constant. I mean, because if it is larger coupling constant, you could have a extra boost in the value to fulfill the. But I don't remember well if it is go up or go down.
Yeah, I don't remember it either. But it's interesting.
Okay, that's it, no? No further question, Javier, no? Okay. So thanks again, Catarina. It was a
Thank you.
pleasure to have you.
Thank you.
So yeah, thank you all. So see you in 2 weeks, 2 weeks time, I think. Thanks.